wet, so I think it was over. Yeah, you seem to have enjoyed all the technical. So today we've got another full day of lectures and the what is the lecture one? The easy one will be there.
Mine's open now, my part's open now.
Okay. So multiple things going on. For those of you who maybe might have seen the next copy, you find these new identity stickers. They're also up here. You want some, grab some. I have some more. But they're there. They're stickers. They're usually very popular, both with the adults and the kids. The first speaker of the day is Zachary, who is going to give us an overview about BlackHoles at home. The toolkit to run BlackHole simulations on your own laptop at home. Previous screen saver. Go ahead.
Great. Thanks, Roland. Yeah, thanks everyone for showing up today. So as promised, I'm going to talk about BlackHoles at home, but I really want to couch this presentation and tune it to the audience, right? We're all interested in the Einstein toolkit. We hear the Einstein toolkit meeting. I want to share the linkages between BlackHoles at home and the Einstein toolkit. So start up a long time ago in a galaxy far, far away, namely Illinois, University of Illinois. Back in 2005, that's when I guess I could start calling myself a budding numerical relativist. I joined the Illinois Numerical Relativity Group as a PhD student. That was led by Professor Stu Shapiro. My first project was to port the code that was originally in the DAGH algorithm, which was an early AMR implementation. Oh, this looks like there are comments. Hopefully they can hear me. Just a sec. Oh, they can. Okay, so the comment is not about I can't hear. Okay, excellent. So I came into the group having just graduated from Stu Shapiro's general relativity course. I was always interested in doing computational physics. In fact, as of early 2005, I would consider myself a budding lattice QCD person, working on theoretical high energy physics instead. But I always had a love for astronomy, astrophysics. I got a minor in astronomy when I was an undergrad. So my first task as a member of the group was to port the entire code base to, well, what was a primordial version of the Einstein toolkit. It was known as Cactus. And it's unigrid, single Cartesian grid driver, PUGH. And after I ported it, I hit the ground running. I read some of the early BlackHole neutron star and co-led some of the first magnetized binary neutron star simulations performed by the Illinois group. And we used the moving puncture approach, which really came into form starting in about 2005. Moving puncture approach was one of the two major approaches that were discovered in 2005 to be capable of simulating binary black hole mergers. That really sparked a revolution in our field. The moving puncture approach to this day remains the most popular approach for performing compact binary merger simulations and performing simulations involving black holes. And part of this was in collaboration with Josh Faber, developing the moving puncture approach to simulate moving black holes moving on numerical grids in the presence of matter and magnetized matter. I was also involved in some of the early turducken work, as it's now called. And it's pretty remarkable if you think about it. These compact binary merger simulations were performed on single Cartesian grids. So imagine that, a compact binary simulation in a single Cartesian grid. We had a trick up our sleeve, though. We used a technique known as fisheye coordinates. That was a coordinate transformation that we would apply such that the highest resolution was in sort of a spherical region around the origin. That's where we put our neutron stars or black holes. And then we would have this transition where it would lower the physical resolution. So it's sort of a mapping from Cartesian to another curvilinear coordinate system to make all of this possible. It was not cheap. This was very, very expensive to do, and it was the expense was a strong motivator driver for us to migrate to the carpet AMR infrastructure, which had at that point only recently been developed. Roland, do you remember when the first version of carpet came out?
Before I joined.
Before you joined. It had to have been maybe only a couple of years old when I added the AMR support to the Illinois Groups Code. Around that time is when I finished my PhD. Part of my PhD work really focused on black hole neutron star mergers, the mixed binary, as they say, which I felt greatly vindicated over the past year with the first very good black hole neutron star merger observed by LIGO. Very exciting scenario. I also was behind the first 0.99 spin moving black hole evolutions. And I developed at that time a new vector potential based GR-MHD code because it meshes so well, pun intended, with the carpet, with AMR, basically. The idea being you could use any interpolation scheme you like at refinement boundaries and maintain the divergencelessness of your magnetic field, using vector potential based approach. And that ultimately evolved into Illinois GR-MHD, which was my first real contribution to the Einstein toolkit. And it happened when I was finishing up a postdoc, and the paper came out after I had already started as a faculty member at my former institution, WVU. In 2017, I, in collaboration with Maria, actually, and a couple of others, developed Giraffe, the first GR-FFE code in the Einstein toolkit, the first open source GR-FFE code for dynamical spacetimes. That still lives. Our Giraffe still lives in the Einstein toolkit to this day. 2018, I developed NERPI, and we'll see one of the motivations for developing NERPI. But one of the core functions of NERPI is to actually generate Einstein toolkit thorns automatically. And if he hasn't already, Steve will hopefully, if he's feeling well enough, tell us about using NERPI to generate Einstein toolkit thorns automatically. And finally, kind of see it, but I'm proud to say that as of 2020, I've been a co-PI on the Einstein Toolkit grant, and I hosted this workshop in 2022 at University of Idaho, my current institution. So I want to talk about motivations behind Black Holes at Home next, and sort of tie this into the toolkit, make connections to the toolkit whenever possible. So the Einstein Toolkit is a remarkable framework for performing general relativistic astrophysics simulations. So let's talk about the importance of modeling both gravitational wave and multi-messenger sources. So let's say LIGO, we went yesterday and saw LIGO Livingston, amazing, amazing feat of human engineering. LIGO detects a gravitational wave from either a black hole or neutron star binary. We were told yesterday that the LIGO project has so far costed about $1.2 billion. And so the billion-dollar question that we're trying to answer with LIGO is, after detecting the gravitational waves, we want to get science out of them. Gravitational waves contain important information about some of the most extreme phenomena in our universe, the collisions of black holes and neutron stars. And the answer to the question, what exactly caused this wave and how did it happen, can lead to amazing insights into extreme gravity, extreme matter, nuclear matter, beyond anything we can reproduce in the laboratory, pushing theory beyond current limits. And that is where new science historically has always hid, underneath observations beyond where we had previously observed. So to advance science, the idea is we compare these hard-fought observations with theoretical predictions. And these predictions are what keep most of us in a job to this day. They have to perform ideally with numerical relativity, you have to span observational and theoretical uncertainties. So it's extremely important that, yes, of course it's important that occasionally we perform very high resolution, very expensive simulations, sort of one-offs. But even more important, we need to generate catalogs of simulations so that we have a nice corpus to which to compare our observations against and extract as much science as we can from the wiggles that nature provides, known as gravitational waves, also electromagnetic waves. Okay. All right, so okay. All right, so let's talk about what a gravitational wave looks like from a compact binary merger. The gravitational waves sap the very energy and angular momentum, keeping the compact objects apart, bringing them into what I lovingly call a relativistic death spiral to collision. And here's what a gravitational wave looks like. You see, as they're farther apart, the frequency is lower and the amplitude is lower because they're moving smaller. They're moving at a speed v over c smaller than 1, always smaller than 1, but much smaller than 1 over in the very early end spiral. But as they get closer and closer, the black holes, for example, can reach velocities of up to, or speeds up to about 0.5 times the speed of light right around the time of merger. So here's what you might see from a simulation of the gravitational waves from a simulation of colliding black holes, emerging binary black holes. This would span about 200 milliseconds. The wave amplitude increases. The wave amplitude is the vertical axis, and it increases along with the frequency. This is known as the chirp signal. And if ever anyone asks you about what you do and you work on gravitational wave science, it's very important to mention that gravitational waves encode important information. They contain information. They tell us the story of this incredibly energetic and violent event where neutron stars get ripped apart, black holes combine to form more massive black holes, emitting more energy than all the electromagnetic energy of the visible universe from all the stars combined in the visible universe. It's truly a remarkable event. These are truly remarkable events. So the very early end spiral, when it comes to theoretical modeling, we can actually model this using perturbative solutions to Einsteinian gravity. And these are generally involve solving ODEs. Einstein's theory of general relativity, of course, is a coupled very nonlinear PDE, set of PDEs. So this is something you can perform on a desktop computer if you like for the very early end spiral. But during the late end spiral and merger, when the gravitational wave signal is in principle the strongest, these perturbative solutions break down and we need numerical relativity. That's when the observers knock on our doors and say, hey, we have an observation, not really, but figuratively. We have an observation. Would you like to compare? We'd like to compare it with full general relativistic solutions and get deeper insights into what it is that we observe. But it's not easy, and it's never been easy in numerical relativity. Einstein's equations are no joke. And we have to reformulate them for the computer. They exist in their original form as a beautiful description of space-time, a four-dimensional thing. Space-time that describes the curvature of induced by matter and stress energy in the universe for all time, everywhere in the universe. We have to reformulate Einstein's theory of gravity for the computer such that it's stable, even when simulating black holes, when Einstein's equations literally break down and you can find infinities at the physical singularity. And also, we need to rewrite them in such a way that they're reliable so that we understand our numerical errors and they are small compared to observational uncertainties. And the real key to solving this, the real challenge, I should say, to solving this, addressing this challenge is the equations are complex. Solving the two-body problem, something you can do in Newtonian physics on the back of an envelope, took 90 years in GR. The year I joined, first started in the field was when that was solved. Thank goodness, I didn't have to worry about that. But yeah, Einstein's equations written in a very, very compact form, G equals C equals 1 units. You can express it like this. And the most popular technique for rewriting Einstein's equations looks something like this, plus or minus a couple of terms. By the way, this has T mu nu equal to 0. So it's actually a much simplified version beyond this. That also contains no equations for solving hydrodynamics or GRMHD. All right, so that behind us, which of course was a remarkable feat, 90 years in the making. The next challenge that we have to address when modeling compact binaries is a dramatic orders of magnitude disparity in physical scales, from the sharp gravitational fields, rapidly changing gravitational fields near neutron stars and black holes, to the long wavelength gravitational waves far from these compact objects. And in fact, gravitational waves being a weak field phenomenon, we can't extract them right at the binaries. We actually have to let them propagate into the weak field region to get an accurate theoretical prediction for what the gravitational wave should look like from simulation. And finally, this is a mathematical complication, but it's a very, very important. And it is, we do not have good outer boundary conditions in our simulations. At best, we have approximate outer boundary conditions. So generally, the strategy is you just push the outer boundary very far away to mitigate its effects, prevent the approximate outer boundary conditions from poisoning the region of physical interest. And it is addressing this disparity in physical scales that is behind the idea of black holes at home, and what black holes at home aims to do extremely efficiently. So why black holes at home? Well, I sort of hinted at this earlier in my talk, but to really drive the point home, it's an endeavor known as parameter estimation. That's where you compare each gravitational wave observed against millions of theoretical predictions. I wish we could perform millions of numerical relativity simulations, but what happens is you start with these catalogs, and then some folks come by and they for example, could train an AI to predict what a gravitational wave would look like between this set of parameters and say that set of parameters, and give you the prediction in between. So there's a complex sort of interpolation that takes place. But the bottom line is these predictions have to be built on catalogs of binary black hole simulations or binary black hole observation. It performed in full numerical relativity. So catalogs like this, generated by, unfortunately, the citation here is missing because of the silly Zoom, but this was produced by the audience, one of their early catalogs. And we live in a very scary time for the fields of numerical relativity. We know that when the next generation gravitational waves detectors come online, our catalogs are going to be our parameters that we extract from the observations. The error bars are going to be dominated not necessarily by the observations, but by numerical relativity itself. We actually need a factor of 10 more accuracy, better accuracy, and of course, larger catalogs to minimize interpolation errors from those approximates, gravitational wave approximates. You know, I take my word for it. You can read some of the amazing works that drew this conclusion. So the black holes at home's goals are twofold. And it is to reduce computational expense for each binary black hole simulation and improve accuracy. Normally, to improve accuracy, you just increase computational expense. You scale out from 1,000 cores to 10,000 cores or something like that. So really, the goals here make black holes at home a doubly difficult project to make successful. All right, so let's talk a little bit about part of how we do it. So in terms of efficiency, we aim in black holes at home to address this modeling challenge in a way that is done more efficiently than numerical relativity codes of the past, even current numerical relativity codes. So what you have to understand are some very simple facts. This talk is meant not just for experts, but also non-experts, because I'm sure there's some non-experts in the audience. So we perform numerical relativity simulations on numerical grids. The numerical solution, you remember all those variables that you saw in those equations earlier? Well, those actually correspond to values that you store in memory at each grid point. You need denser grids to model sharper features. So you're going to need higher resolution around and inside black holes and neutron stars. And another important fact that it kind of requires a high level computational physics class to understand, and that is the simulation speed, the rate at which you can advance the simulation from one step to the next in time is proportional to the minimum distance between grid points. This will come in this will be a very important fact as we talk about black holes and all. So bear that in. All right, so I hope what you can gather from this is the fewer the number of grid points, the lower the computational cost. And if you have less computational cost, you can either with the same cost, unlock more simulations or add more physical realism. But really a key consideration must balance the number of grid points versus the simulation speed, which is going to be based on number of grid points versus the minimum distance between grid points. We'll see what that means in a minute. So how do we address this? The most popular technique in numerical relativity is AMR, adaptive measure refinement. There is a wonderful AMR driver within the Einstein toolkit known as Carpet. I've used it much of my career. I've implemented codes in Carpet, as I mentioned at the beginning of my talk. And how it works is it resolves the disparate length scales with nested Cartesian grid cubes of differing grid spacings. When you zoom in, you see indeed resolution is highest where the fields are the strongest inside black holes. So this would be like delta x equals delta y equals delta z on the finest grid, 2 delta x equals 2 delta y equals 2 delta z on the next coarser grid, etc. And you just have low resolution where you model the gravitational waves. So out here, great. So that seems to address the second modeling challenge. And the third, you just add coarser grids to push the outer boundaries very far away. Great. So it looks like we've addressed all the major issues. So what's the problem? Well, the problem is it's inefficient. Adaptive measure refinement is inefficient, especially in its more primitive forms. We just have moving boxes, for example. So what do I mean by inefficient? And some of these inefficiencies hold for all Cartesian AMR approaches. For example, black holes and neutron stars. They don't look very box-like, do they? In fact, if we were to stand at the center of a black hole, not recommended, but if we were, what we would find is that if we look out radially, we would notice that the gravitational fields are changing very, very quickly. They're very sharp in the radial direction. So that means we need a lot of sampling in the radial direction. But if we fix a radius and we look at how the gravitational fields change versus angle, we would notice that they don't change very much at all. And so we don't need as much sampling in the angular directions as the radial direction. So you need high sampling in the radial direction. Now, here's the question. On a Cartesian mesh, which direction is radial? Is it the x direction? Yep. How about the y direction? Yeah, that one too. Uh-oh. How about z? It's even worse than that. It's even radial along the longest diagonal of a Cartesian grid. So if you have a resolution delta x, delta y, delta z, all equal, then your lowest resolution is along the longest diagonal, which is √3 delta x. So all directions are radial. You need high sampling in all directions, even along the longest diagonal. If instead you were able to model this in a spherical grid, you could reduce the computational cost significantly because you could put most of the resolution in the radial direction and less in the angular direction. So very rough, conservative estimate, maybe you could drop the number of grid points in the angular direction by a factor of a bit over 2 or something. So you get about maybe a factor of 5 efficiency boost on a spherical. The same story holds when we zoom out and look at the gravitational waves. Again, they're changing most rapidly in the radial direction, and in the angular directions, they don't change much at all. So exactly the same argument could be made. If we had a spherical grid in the wave zone. Another fact is these discontinuous jumps of resolution of factors of 2 as you move out actually cause a lot of problems. We'll talk about this a little bit later in the talk. But gravitational matter fields, they're mostly smooth. They don't change their physical length scale discontinuously by factors of 2 as you go out. So if you could have a grid structure that had smoother transitions in resolution, you could save a lot. And I'm estimating here, crudely, maybe another factor of 4 efficiency boost if you use something like a bispherical grid structure. We had smooth, logarithmic radial coordinates away from neutron stars or black holes. So here's the AMR grid. And what first inspired to, okay, let me first say, more efficient grid structures, like I said, just to summarize, smoother transitions in resolution and exploit near symmetries. It wouldn't shy away from singular coordinate systems. That is, coordinate systems that exhibit coordinate singularities, like in spherical coordinates, the z-axis, r equals 0. In cylindrical coordinates, the z-axis. So it would build on work, pioneering work done by Brown and Bogart et al. in the around 2010 era. We came along a bit later in the game, and we were able to build on this and extend it in collaboration with Bogart to extend this approach to spherical-like, cylindrical-like, Cartesian-like coordinate systems using what's known as a reference metric formulation of Einstein equations. It was demonstrated that you could perform numerical relativity simulations by these folks. You can perform numerical relativity simulations in spherical coordinates as robustly as Cartesian, which is a remarkable thing to be able to say. This is what drew me to this, this approach. And what really sort of motivated this was the fact that I know a lot about what's in the Einstein toolkit. I've been working in the Einstein toolkit pretty much my entire career. And there is a thorn in the toolkit known as two punctures. Two punctures is absolutely a remarkable piece of software. It generates initial data for a binary black hole system in a beautiful grid structure that looks like this. This is a single patch, single grid. Put one black hole at one focus, you put the other black hole at that focus. It's axisymmetric about this axis right here. And you can generate initial data for binary black holes with two punctures in only of order 100 or hundreds of megabytes of memory. So my thought was, well, how about I apply these techniques that were developed for spherical coordinates or cylindrical coordinates to two punctures coordinates. Also known, it's a relative of prolate spheroidal coordinates. And I did. In NURBY, I generated Einstein equations for two puncture-like coordinates, prolate spheroidal coordinates. And I successfully solved the wave equation on this grid structure. Hooray. But that's just one step, right? Next step is generate Einstein's equations on that grid structure and try to solve them. It was violently unstable. It's the only coordinate system we were able to find that uses a reference metric that results in violently unstable solutions. Like smack you in the face, your nose is bloody at the end of the day. More like at the end of 6 months. We spent 6 months trying to figure out what was going on wrong here, and it remains a mystery of the universe. So if you are feeling excited about this mystery, by all means, you can download NURBY. You can pip install NURBY. You can tell it to output in what we call cinch sim TP coordinates, which is the TP stands for two punctures. And you can try to do simulations yourself and find the same issues that we found. And maybe with enough inspiration, you can solve this mystery. But the thing is, if you look closely at what the grid structure does near the focus, it's not exactly ideal for black holes, right? It doesn't look very spherical, does it? Especially if you look along these coordinate lines. It doesn't look very spherical around the black holes. One really nice feature, though, is this outer grid, really, it does, in the limit r goes to infinity, become perfectly spherical with a logarithmic radial coordinate. Logarithmic radial grid spacing increases as you go out. But it's not great here. There's a tremendous amount of grid focusing at each of these foci. which, as I said before, right, the smaller the simulation time step is proportional to the minimum spacing between grid points. That spacing becomes very tiny, like centers of these black holes. So the bottom line is, yeah, it felt bad that we weren't able to solve this puzzle. But at the end of the day, it's not that efficient anyway. And so what we moved on to after that was this grid structure, which I call bisphere grids. We know that we can solve Einstein's equations for black holes on spherical grids, in spherical coordinates. That was demonstrated by Baumgarten collaborators back in 2012. And so I thought, well, what the heck? We'll just put a grid here. We'll have two patches. All we have to do is communicate information bidirectionally between the two grids, and we can perform a binary black hole in spiral. And I did. It was, in fact, a factor of 20 more efficient in memory usage. But there was a problem, and that problem was the grid spacing goes to almost zero as you go into the black holes. And when it comes to simulating black holes with the moving puncture approach, you do simulate all the way inside the black holes. So we do our sampling of space-time deep inside these black holes here, where the grid spacing is basically going to zero, and our time step is going to zero as well. So what happened was our simulations were still about a factor of 50 too slow for what we need for a volunteer computing project like Black Holes at Home. It would take on a consumer-grade desktop about a decade to do a single binary black hole in spiral and merge it. And I would hope in that decade we would come up with much better techniques, and that would pretty much deprecate all of that infrastructure anyway. So on to the next approach. And it was this. So I call it the hybrid grid structure. The idea being it sort of takes the best of both worlds. It's a spherical domain out here and a big old honking Cartesian grid in here. Because there's no R equals 0 focusing of grid points, we were able to get away with a factor of 100 larger time step. But we should be worried. What about the memory usage in this big honking Cartesian grid? I mean, this harkens back when we were using fisheye coordinates. Remember, I talked about that earlier. We were able to do it, but it was very expensive. And really the question is, will it even work? Because this is a grid structure that had never been tried. Again, pure spherical grid, pure Cartesian grid. So here I'm going to show you that, in fact, it did work. I'm showing you the inner Cartesian grid here, basically. And you see the two dark spots here. Those are the black holes. They do their in spiral. They merge. We actually continue the simulation again for a while because the gravitational waves are weak field phenomena. So we need to actually model gravitational waves as they propagate far away, and we can extract them reliably to get theoretical predictions from this simulation. I'm going to go ahead and advance. The movie's still playing. You can't see much. Gravitational waves are far away and getting farther. And so what did I do? Well, I compared the result from the simulation, the gravitational wave prediction, against a trusted code, the Einstein toolkit, of course. And I found, to my huge relief, because this took months of development, I can't stress enough, this is not easy to develop a new numerical relativity code. What's that mean? One does not simply, right? One does not simply just write a numerical relativity code from scratch. So comparing with the trusted code, seeing that the gravitational waves overlap perfectly, they're indistinguishable, was an enormous relief. And that trusted result with the Einstein toolkit, it was performed on Cartesian AMR grids. It took about 4 HPC nodes. It was relatively inexpensive because the two black holes are pretty close, and it was rather low resolution. But it required about 30 gigabytes of memory on an HPC cluster. So what about the new simulation? Well, remember I said it's very inefficient. We have this big honking Cartesian patch in the middle. Were we able to perform the simulation? Obviously, yes. Did we need an HPC? I have a good answer to that. No, we didn't need an HPC. In fact, we didn't even
10 minutes.
A desktop computer. I did it on my now dead 2016 cell phone. I did this simulation on my cell phone, and only about 2 gigabytes a minute. And screenshot, or it didn't happen. It was right there. So the cell phone didn't last very long. I had this, like many of us do, rubber protector cases on them, which act as excellent insulators. And the old version of Android at the time didn't downclock the CPU when it got hot. So I pretty much melted my cell phone doing this. So, yeah, please.
How much physical time?
Yeah, about 4 days. You can see it running here at the rapid pace of about 1.4 M per hour. This is about 100 M simulation. Yeah. Oh, yes, sorry. The question was, how long did it take physical time to finish the simulation? And yeah, my cell phone was out of service for 4 or 5 days, physical days, wall clock days, while I was doing the simulation. So great question. Yeah, so again, the problem with this grid structure, it's very, very inefficient. It really only works well when the two black holes are close to merger. That said, what it tells us is when the two black holes do get close to merger, we have a grid structure that we know will work and will also not take too much memory. So kind of mixed bag, right? We really want to perform simulations though from larger separation. That's where things get much more interesting. And so Isaac Newton, during the pandemic of his time, invented calculus. I, during the pandemic of our time, invented a way to solve Einstein's equations on a 7-grid structure that built on everything I'd learned previously. Namely, when you have a spherical grid, do not allow sampling near r equals 0. So inside this big spherical grid, which is the wave zone grid, I have a couple spherical grids in here. Inside those spherical grids, we have little Cartesian patches. Again, you can see no r equals 0 focusing, fully dynamical grids. They co-move in spiral, they co-precess with the black holes, and it works great. And by the way, this is not ordinary Cartesian AMR that we know and love. This is actually a coordinate system known as, I call Cinch Cartesian, which enables us to get about a factor of 8 improvements in resolution from the center of this grid to the outer grid here, with only one level of refinement. This is very important because we have a very small memory budget. I often say, black holes at home, we can solve binary black hole problem on it within 3 gigabytes of memory or your money back. So that's the idea. 3 gigabytes of memory, we will perform the simulation. So there we go. As I said, about 3 gigabytes of memory, and I've demonstrated that it works. I compared against I performed the same simulation at Q equals 6K. So, okay, this is 6-to-1 mass ratio performed on the desktop computer with black holes at home compared to the same wave, the same simulation, same physical scenario, courtesy SPEC and the SXS collaboration. And you can see the dominant mode agrees very well, even though we don't have eccentricity reduction, they do. So it looks pretty darn good, the overlap. Here's the amplitude of the L equals M equals 4 mode. You notice something interesting here, that the SXS result, the SPEC result, is a little bit noisier, especially early in simulation. And L equals M equals 8 is something that is very difficult to extract from a Cartesian AMR grid. And I think only the SXS collaboration have generated, usable L equals M equals 8 modes. We're actually significantly less noisy than even SPEC. So very exciting result there. In 2022, I rewrote our multi-patch infrastructure to handle mergers. So you notice that previous slide didn't go all the way to merger. And so how I did it was a sort of Lego building blocks approach. So literally there's to handle 3 spheres, 3 overlapping spheres. There's like 3,000 lines of C code. A Cartesian AMR like inside another Cartesian AMR like patch. That was about 2,000 lines of code. That was a weekend. Spherical AMR, it's a spherical like inside spherical like. That wasn't too difficult either. Cartesian like inside cylindrical like inside spherical like. So that's sort of how I built the grid structures as of 2022. And when I perform these simulations, you can see on the left how the grid structure evolves over time. So this is that 7-grid grid structure here. This is about Q equals 1 case, and you can see the grid structure changes very rapidly as the black holes get closer and they merge. And one thing I was very worried about was, well, when the grid structure changes so
5 minutes.
When a grid structure changes so radically during the in-spiral and merger, surely that means that the constraint violations, the numerical errors, are spiking around that time as well. So that's something I was worried about. Here's the absolute value of the log basis error. They have a 20 constraint violation. The darker, the smaller. So you'll notice they in-spiral. The constraint violations are pretty low. And you notice they don't actually spike at all. And that's partly because Cartesian AMR grids, while they are inefficient, they add a lot more grid points in places where you didn't have them before. Your numerical errors are actually pretty well under control. That was a very big movie. We did convergence tests and as well, demonstrating the 7th order convergence. That is the same order of convergence of numerical errors to 0 as the interpatch interpolation form. And in 2023, I performed hundreds of binary black hole simulations. I really improved the robustness of many of the algorithms within black holes at home. And I performed hundreds of binary black hole simulations, reproducing SXS catalog simulations. You can see this is the precession plane. So this is the z-axis. This is the XY plane here. This is the XY plane. So you can see that some of these systems are very strongly precessing. And the unfortunate thing was, as I said before, one does not simply write a numerical relativity from scratch. I found an instability in about 20% of cases. So I'm going to talk about what I've done over the past year now in just a few minutes. So let's start with improved moving puncture techniques. So these were developed in black holes at home. It's wonderful to have a code where you can just run one experiment on one node. So if you have 100 nodes, you can run 100 different ideas about ways to improve the accuracy of moving puncture evolutions. And the idea is these improved techniques incur minimal cost, additional cost. They're infrastructure agnostic. I demonstrated their efficacy in this paper, which you can find in the archive, with the Einstein toolkit, demonstrating that they're infrastructure agnostic. Anyone who uses the moving puncture approach, in principle, could benefit from these, not just for binary black holes, but also perhaps binary neutron stars. And so the focus of these techniques really is to curtail the development and impact of a sharp feature in the lapse evolution. Lapse is one of our gauge quantities that results in, as the simulation progresses, a 10 order of magnitude increase in the Hamiltonian constraint violation. And so there's a lot that we could improve potentially. So let me show, I think it's best illustrated with this movie here. So we have okay, so let me first show what's going on. So this here is the radius that actually
2 minutes.
I get it. This is the x-axis. These dashed lines here, this is a simulation performed in the Einstein toolkit on Cartesian AMR. This is a refinement boundary right here. Each of these dashed lines, vertical lines, are where refinement boundaries are. And you'll see that the control run, which is a standard moving puncture approach that we all know and love and many of us use, you'll see this sharp lapse feature. This is the lapse. This should be a constant, r times 1 minus alpha. 1 minus alpha goes like 1 over r. This should go to a constant in the weak field. What you see is a big oscillation, very sharp oscillation, a sharp feature in the lapse that as it propagates, remember this is higher resolution, factor of 2 lower, factor of 2 lower than that, factor of 2 lower than that. Eventually this wave is going to get reflected off of these AMR boundaries. And then compare that to after all the improvements that I implemented and tested in black holes at home. Notice, look at the reflections. It's crazy. Look at that.
1 minute. Please conclude.
This is actually the gravitational wave. And look at this. Look at all this noise. Now you might argue, well, this is just a gauge wave. This is not a physical wave. The problem is you look at the right-hand side of the evolution equations for the physical quantities, and you're going to find, for example, Laplacian of the lapse there. And so it all couples. It all couples together. Errors
30 seconds. Please conclude.
Will contaminate physical quantities, including our constraint violations. So the impact of these improvements on the strong field, Hamiltonian constraint, about a factor 2 orders of magnitude smaller, momentum constraint, 3 orders of magnitude. In the weak field, it goes bananas. Hamiltonian constraint violations, 5 orders of magnitude smaller. Momentum constraint violations, 2 orders of magnitude smaller. And perhaps the most important takeaway is that previously noise-obscured subdominant gravitational wave modes that might be detectable by next generation gravitational wave observatories can now be extracted. They were too noisy before. Now you can actually extract them from the simulation, from the predictions. And I also have improved convergence properties. So these factors that I quote, if you increase the resolution, the gaps grow. These factors increase. source. I'm going to propose its inclusion, an improved version of by call forms for the next Einstein release in November. All right. I also open sourced BlackHoles at home, mostly open source, everything with the multi-patch infrastructure. BlackHoles at home is a NERPy project. NERPy 2.0, that was my summer project last summer. And we're all better off as a result. We now pip install NERPy. It's a lovely thing. And modernize NERPy and address community feedback. Steve Grant had no small role in that feedback, as well as other users. So in development is a general multi-patch approach that's enabled district structure, for example. So general multi-patch, remember I told you about 20% of the simulations crash. It happens at the outer boundary of the simulation domain. And the reason it is happening is there is interpolation sometimes when we do these simulations of black holes. We actually interpolate all the grid points as the black holes coordinate, the black holes coordinate, all the way out to the outer boundary. And what happens is the interpolation is sometimes amplified by this exponentially right on the z-axis of the sphere grid near the outer boundary. And we can remove the instability if we adjust the regridding frequency to minimize how the distance between source and destination points in that interpolation. The solution is very simple. I don't want to have to tune the regridding thresholds. So instead, we're just going to do this. And cover the inner grids only, leave the outer grid fixed. And it works. I've validated it for the wave equation, and now this summer I'm going to be working on the Einstein's equations with this approach. All right, so a lot of progress has been made, and it's going to be a busy summer. So hopefully we'll have the volunteer computing project going in the next year or so. Fingers crossed, it's ready when it's ready, and when we can all trust it. So thanks everyone, and I'm happy to take any questions.
So you have 12 minutes for questions.
Hey, hold on.
Which shall we off the stage?
Good.
The simple one, this is not using BSS, the movie function.
Yes.
Okay.
That's right. This is in a movie function. Thank you. Yeah. Right. Yeah. So so the question is, what is the problem with solving Einstein's equations in singular curvilinear coordinates like spherical coordinates without using a reference metric? So what a reference metric does is, at least the reference metric prescription that was found to be stable, what it does is so Einstein's equations, first off, are a tensorial description of gravity. Tensors are like vectors on steroids to some degree. Vectors and tensors are have in spherical coordinates have components that blow up or go to zero at coordinate singularities. Like literally, they will go to infinity at coordinate singularities. So, but the thing is, we understand analytically how they blow up. So if we move to it, and this is something we all learn when we go to an orthonormal basis, and when we learned about this in our E&M classes, for example. So effectively what's done in this reference metric approach is you move to an orthonormal basis, basically, so that the vectors and tensors no longer diverge or misbehave at coordinate singularities. So thank you. Yeah.
Sorry.
Yeah.
Yeah, sure. But with this body patch coordinate.
Yeah, good question. So actually, yeah. So the question was, in the multi-patch algorithm, there aren't coordinate singularities. Actually, there are still. The z-axis of every grid that I showed has a z-axis. Every spherical grid I showed has a z-axis, and the coordinate singularity still exists there. So it does. I am working on multi-patch approaches that don't have coordinate singularities, but that's another talk for another day. Yeah. Yeah. Yes, yes. So the question is, what's incomplete? What still needs to be done in BlackHoles at home? And that's beautifully illustrated with this little sort of corny movie here, as you can see. What remains to be done is solving Einstein's equations on a grid structure where there's a sliding boundary here. This is not something that my old Lego building blocks approach could handle. Was a sliding grid boundary between these inner grids that sample the strong field and this outer grid that samples the wave zone and the outer boundary. So that's what's missing. Now I said, and I really wanted to, I didn't have time, actually show a movie that demonstrates this works for the wave equation. I literally solved for a Gaussian wave pulse starting at the center here on this grid structure, which is the worst grid structure you can imagine, at least in this region, to sample this wave, and it was stable and it converged properly. So yeah.
Thank you. Great job.
Thank
So when you suggest that, are you suggesting this as an alternate for rapid pressure environment? Or are you suggesting it as an extension?
I'm not suggesting it as an extension to the Einstein toolkit. However, we do have, we really would like to have, for say, a Cartesian AMR boxes in here, maybe in the CarpetX infrastructure, actually to contribute the multi-patch infrastructure needed to make this a pure spherical grid. There is work being done by Lucas. What's Lucas's last? Lucas, what's that?
Sanchez.
Sanchez. Excellent. Yes, awesome. Yeah, Lucas Sanchez. Sorry. There he is. Awesome. There he is. Raising his hand. Okay. Okay. Yeah, Lucas Sanchez. Yes, who's been working on a 6-patch representation of a spherical coordinate system known as cube spheres approach. So the idea would be we would sort of build off of Lucas's work. Just have a single patch out here, just plain Jane spherical coordinates. I really do want to contribute that to the Einstein toolkit and CarpetX once we have the multi-patch scheme completely ready to go.
So when you did the simulation of the home, did you have the cactus installed? And how would that work?
Yeah, so when I did the simulation on my phone, the question was, how did it work? I didn't use the Einstein toolkit on my phone. I did that simulation for the Einstein toolkit on an HPC. It was the BlackHoles at home that worked on my phone. And by the way, you can do it with an Android phone. Apple will not allow you, in their infinite wisdom, to compile and run executables, but to use run your own code on the CPU. Like, I don't know, it drives me crazy to think that I don't have the power to do that. But on a Android phone, you download the app called Termux, T-E-R-M-U-X, and it will basically install a very lightweight version of Ubuntu, which has a Clang compiler, and you compile BlackHoles at home and run it on your phone. Again, be careful. If you have insulation around your phone, you might want to remove that. Actually, newer versions of Android will downclock your CPU, so it won't burn up like my phone burned up. So it'll be relatively safe. Knock on.
We've got 2 online questions and 5 minutes. So the first question, which came in earlier, is by Steve. He's asking, do you have a feeling of how much compute power it would take to do a waveform usable by LIGO with BlackHoles at home? And have you talked to LIGO people about using this?
Great question. Yeah, so BlackHoles at home, the simulations that I showed earlier, with all the beautiful trajectories. Actually, those were some of the results from those simulations, those hundreds of simulations that I performed. I performed them because I'm in a debugging stage right now on the fastest CPUs I have available, which are some HPC nodes. They ran in about a month, 2000 M, I think, of simulation time. The idea is when we get to volunteer computing project, it's about throughput. It's not about performance. So if we want to do a rapid follow-up, that's where a sister project to BlackHoles at home known as Superb. The supercomputer-ready version of BlackHoles at home which is being developed right now. You can actually pip install NERPy and get its Charm++ parallelized version for a single patch in BlackHoles at home. You can actually perform simulations right now, and it scales very well. We're very excited about this. It's a project led by one of my postdocs, Nishita Nadu. But that's what we plan to do for rapid follow-ups. That's, I think, the most important thing for, say, next generation gravitational wave detectors, other than creating these gigantic catapults. So catalogs generation. So when we talk about mass ratios of about 4 to 1 and higher, black holes at home is roughly a factor of 7 more efficient per CPU hour than the Einstein toolkit with carpet with those sort of mass ratios. And I'm working on fixing, there's an inefficiency in black holes at home for Q equals about 1. The bottom line is Q equals 1 all the way to Q equals 6. Black holes at home runs at about, Q equals 1, Q equals 4. Black holes at home runs at the same speed. It should run about 4 times faster at Q equals 1 if all things are equal. And the reason it's a silly one, the reason is for near equal mass, the smallest grid spacing is up here and right here and right here. It's not actually at the center of the high resolution grids. It's a silly inefficiency that I'm working to fix. So that will be coming in the near future. But yeah, I hope that helps to answer the question verbosely and like any good professor should.
Okay, last question is Lucas. If you're speaking, Lucas, we can't hear you. Type your question in the chat and I can read it.
That would work. Oh, we have a couple of questions in the audience.
I was super follow statements. How are
That's exactly what our goal is with Superb. Our Superb's goal is A, rapid follow-ups, and B, perform simulations of the extreme regions of binary black hole parameter space. I'd like to just say, blurt it out, 100 to 1, Q equals 100 or bust, but we'll see how far we can go. I mean, because black hole syndrome is already already has so few grid points, we can't scale, in fact, to millions of cores. But if we can scale to order 10 to 20,000 cores, that's going to unlock some pretty interesting physics. So, great question. Argue that if you can't scale well, sorry. I will repeat the question. Yes. So the comment was maybe the reason is that you can't scale well is because you don't have as many grid points. That's absolutely the case. Absolutely. But I wouldn't argue that it's not scaling well. I mean, the scaling should always take into account how many grid points you need in the first place, right? It would be silly to expect that for a grid that has of order 5 million grid points to scale to 5 million cores. Like that is ridiculous, right? You can't just have, it's never going to scale well in that sense. But yeah, so we don't need to scale to that many cores. But what is really exciting about that is with a big supercomputer allocation, we can perform multiple simulations of high mass ratio and not have to just rely on a single hero simulation. We don't have to do hero simulations. That's the idea on an HPC. We could just do multiple of these. And like I said earlier in my talk, it's fine. It's great to do these hero simulations from time to time where we do one big simulation using a big HPC or something. But if we can do the real science, I think, comes from catalogs because nature is not going to give us that one parameter. It's going to give us something in between a set of parameters. So I think it's more useful in that sense that we're not so quote unquote scalable to millions of cores.
And we're just on time.
Cool.
14 seconds left. Let's next slide once more. So Zach is around. There should be fresh coffee on the outside. Have a half-hour break. And then you would